All right. Welcome back from lunch. Thanks to NANOG for sponsoring that lunch, and welcome back to the 60th Hunger Games. We'll be kicking off this afternoon with Robert Edmonds talking about high-speed DNS logging. Robert.
Hi, I'm Robert Edmonds from Farsight Security. It's actually high-speed DNS logging without packet capture. First off, here's the URL to our website, dnstap.info. It's got all the information or links to all the information about dnstap, so documentation, presentations, tutorials, code, everything is on this one site or linked from it. So here's that URL, including this slide deck. So here's our simplified RFC style DNS overview. We have some DNS protocol endpoints, these stub resolvers, recursive servers, authoritative name servers. Then on the bottom we have these applications and caches and zone data. And basically, an application wants to do a DNS lookup, so it talks to its local stub resolver. The stub resolver then talks to a recursive server, and if it doesn't have the information it needs in its cache, it talks to one or more authoritative name servers, and the name servers have the zone data that's needed, returns to the recursive servers. The recursive takes a copy for its cache, returns the result to the stub resolver, which returns it to the application. So we have this fairly complex flow of data between these protocol elements in the network and the applications and data. And that's the simplified DNS overview right there. And one of the first two use cases that motivates dnstap is query logging. And we zoom in on this DNS overview, and we focus just on the queries between clients and servers. It's going to be between a stub resolver and a recursive server, or between a recursive server and an authoritative name server. And in that case, the recursive server can function as both a client and a server. So here's the query logging use case. We're basically just logging information about the queries themselves. So the IP address of the initiator, the client that sent the query, question and question type, basic information. And there's more other related information that could possibly be logged about queries, like EDNS options, DNSSEC information, performance information, like whether it hit a cache, or if it had to do a cache fill in order to respond to the query. And that last question actually requires more detailed information. So we may have to look at both queries and responses. So the name may be a misnomer depending on whether you're actually logging that kind of information. And the typical implementation of query logging, the in-server implementation, is that the server itself generates log messages as it's going about its normal course of processing requests. And this is generally has been reputed over the years to impact the performance of the DNS server significantly. So the default is off, and you have to go and explicitly turn it on if you want to enable this feature. And the typical implementation inside the server is to parse the request, format it into a text string in some ad hoc format, and then send it to a syslog or write it to a log file. And this tends to impact performance for a variety of reasons. Most of these are implementation issues. Actually transforming the query into a text string takes time. Parsing format strings, copying data, all that, and then taking that text format log message and writing it using synchronous I/O in your worker thread. Obviously has the potential to block progress inside the worker thread. If you're using syslog instead of writing the log files directly, that takes out locks and does blocking writes for every log message. So usually DNS servers will implement their own log file writer. Actually, many different types of servers, not just DNS servers, have their own log file implementations. But even then, if you're using a printf or fwrite style function, that can take out a lock on the output stream, so it's still not ideal. So the usual response to all these performance issues with query logins to do it outside of the DNS server, do it with packet capture instead, your TCP dump or some other special packet capture software. The problem with this is that it performs great because you can do it completely outside of the DNS server, even on separate hardware if you have the right architecture. But it can't replicate state that appears directly inside the packet. So stuff like if the request was served from the cache, well, there's nothing in the network packets that explicitly indicates whether it was served from the cache or not. So the big question is, if we could fix all these performance issues in the server software, could we rely less on packet capture for this particular use case? And this brings us to the second motivating use case for dnstap, which is passive DNS replication, which in many ways is almost the complete opposite of query logging. So we're looking at not the queries from the clients towards the servers, but rather the responses from the authoritative name servers to the recursive servers. And we're focusing on the resource record content rather than the question being asked by a particular client. And there's usually, I divide passive DNS replication into two different deployment options, which I don't have time to go into in detail, but there's one which is below the recursive, up by the arrows by number 1, and then there's the above the recursive, and these two different vantage points have very different characteristics and trade-offs. But the basic idea is that we want to log information about the content of zones. The resource records, the owner name, type in data, and potentially the IP address of the name server. And the idea is to replicate this zone content, usually for anti-abuse purposes. And your typical passive DNS replication implementation is going to, it's going to be packet capture based. It's going to capture the response packets at your recursive DNS server, reassemble these packets into messages, and then extract the resource records that are contained inside the messages. And this, because it's packet capture based, has very little to zero impact on the performance of the recursive DNS service itself. Unfortunately, there's a number of issues with passive DNS replication. Because you're doing packet capture, you don't have access to certain information inside the server. So you have to come up with a way to discard out of bailiwick records, which occur quite frequently in the DNS. You need to be resilient against spoofed UDP responses. So for instance, you don't want your passive DNS replication system to blindly accept any UDP response message simply because it was captured on the wire. And then you have to deal with fragmented UDP packets and TCP streams. You have to reassemble those into the constituent messages and stuff like UDP checks and verification. So you have all these data issues when you do passive DNS replication with packet capture. And the interesting thing is that the recursive DNS server and the kernel and networking stack that's running on everything are actually already doing these things. And so if there were some way we could be inside the DNS server, we could avoid almost all of these issues. So here's our key insights for these two use cases. Query logging, we could potentially make it a lot faster by eliminating all these bottlenecks formatting into text strings and doing synchronous logging. And for passive DNS replication, we can avoid all these state reconstruction issues at the network level by capturing messages from inside the DNS server rather than capturing packets outside of the DNS server. And ideally, since these use cases appear like they would be implemented fairly similarly when you're doing this type of logging inside the DNS server, we should be able to support both of these use cases with a generic, flexible mechanism. So this brings us to dnstap itself. Basically, we're going to add a lightweight message duplication facility directly inside the DNS server implementation. And we're not going to do any reinterpretation or reformatting of the original wire format DNS messages. We're just going to take the verbatim wire format DNS messages and just encode them, potentially annotate them with context, we're going to use a fast login implementation so that we don't degrade the performance of the DNS service. So we're going to use various implementation tricks like per thread, circular queues for each worker thread. We're going to do asynchronous buffered I/O so we don't block any threads from making progress doing their real job, which is to actually respond to clients. And we're going to prefer to drop logging payloads instead of blocking the server if we're under high load and have an excessive amount of work to do as compared to a synchronous system where that can potentially block the server from making progress. So basically, a DNS server has these internal message buffers for processing queries and response messages, sending in and receiving queries, sending in and receiving responses. And so the basic idea is that we should instrument the call site, the code sites in the code where these buffers are manipulated. And once we have a full message buffer with the complete DNS message in it, we should just duplicate it and export it outside of the server process. And we should be able to enable and disable each logging site independently of all the other sites so that we can support different use cases. So there's currently one top-level message type, and that type has 10 different subtypes corresponding to these different code sites for all these different roles in the DNS protocol. So we have authoritative servers, and they can receive queries and send responses, and resolvers can send out queries and get responses back from the authoritative name servers. And there's the clients, forwarders, and stubs corresponding to all these different arrows in the DNS architecture. So you have these red and green arrows, and at each end of the arrow there's a different piece of software, and these all correspond to the different types of messages in dnstap. Here's the architectural overview of a dnstap enabled DNS server. So you have this top block with the dotted lines around it. That's the DNS name server process actually running on your hardware, and it's got these red and green arrows. These are the network messages coming into and out of the server process through the kernel and the sockets layer, and then they talk to individual worker threads inside the DNS server process. And in a non-dnstap enabled DNS server, that would be it. Just have these worker threads inside the process answering queries, sending responses. But then we add dnstap support to this DNS server, and basically we have this, the brown arrow, the dnstap payload comes out of the worker thread, goes onto a circular queue, and then there's at the far right of the diagram, there's a dedicated I/O thread that pulls down the payloads off of the circular queues and actually takes care of sending those messages, exporting those log messages over a socket to a dedicated capture process. So this gets the task of sending these log messages out of the main flow of the worker thread. Then you have this stream of log messages coming over this byte-stream socket into a dedicated capture process. This receiver process gets the log messages in a particular format and processes it, does whatever it needs to. Here it's just writing it out to a log file. So instead of having the DNS server be responsible for writing out the log messages to disk, we've sent it to a separate process that's now responsible for this. So here's what query logging looks like with dnstap. We just turn on the right knobs for the whatever the query messages that we're interested in. Optionally, we could turn on response message logging as well if we were interested in that kind of data. Then we just connect a dnstap receiver to the DNS server, and it does whatever it needs to with that data. Performance impact should be minimal due to all the implementation tricks, and now we have this full, this rich verbatim message content with annotations and metadata is now available. And we don't have to parse any text format logs or anything like that in order to consume it. Then there's the second use case. Passive DNS replication is just we turn on a different knob that duplicates the other type of DNS messages that we need for that use case. Likewise, just connect a receiver up to the dnstap socket, and that's it. And now that once we're inside the DNS server process and doing passive DNS replication inside the DNS server, all these problems that we identified earlier, suddenly they just disappear. So out of bailiwick records, we can, since the DNS server already knows which name servers are responsible for which zones, it can annotate the message with that information. So we don't have to reconstruct that after the fact. Spoofing, the DNS server, it's already been hardened as much as it can against spoofing. So we know that it's past the state table, past the all the anti-spoofing stuff that the server does. We know that that's been guaranteed for a particular response message that comes out of this mechanism, and the various TCP UDP reconstruction issues. Those are already completely handled by the kernel and the DNS server, and we're just duplicating the already reassembled DNS messages, so we completely avoid having to implement any of those IDS-style reconstruction algorithms. This is a fair amount of different components. So there's we have the log format itself for dnstap. We have some different helper libraries for adding support, generating, consuming, or parsing and generating, sending and receiving these log messages. Then we have patch sets that integrate DNS support into the existing DNS software. So it's basically patches to call the right library routines, construct the log messages, and have them sent to a dnstap receiver. And then we have individual capture tools that actually do the reception of dnstap messages and do whatever processing or analysis based on the log data that's being generated. I'm not going to go into too many details about the log format, but it's we use protocol buffers, for the Google protocol buffers format for encoding, which is not quite a standard, but it's fairly widespread. There's implementations for just about every programming language. It's very compact. It allows binary clean fields to be encoded, so we can put the DNS messages verbatim into a protocol buffer message, and it's got explicit support for backwards and forwards compatibility, so we can we can add new types of dnstap logging events without requiring upgrades to all the deployed software. There are a couple of different helper libraries, which I'm mostly going to scope over. Basically, there's an encoding agnostic transport and a transport agnostic encoding, whatever that means. And that adds a few thousand lines of code to the DNS server. Since this is, these are libraries that are being directly called by the DNS server process. And there's the dnstap integration itself. We have plans to, fairly ambitious plans to add dnstap support to a variety of different software that handles DNS messages. You have DNS servers, your bind, unbound, cannot. You have analysis tools like Wireshark. You have various command line utilities like dig, kdig drill, benchmarking tools like DNSperf and ResPerf. Might be interesting to add this support for this interchange format to all of these different tools. And obviously, it could potentially enable more applications by having this interchange format available. So this is a hyperlink to directly to the GitHub repository. We have a proof of concept implementation for the unbound DNS server, which is a recursive DNS server. So it supports the subset of message types that are relevant for that type of server, and adds less than 1,000 lines of code to that server. And that's working. There's a proof of concept implementation for that. Not yet production ready. We're working on that. And there's a dnstap capture tool. It's a similar role to something like TCP dump or syslogd or a flow collector or something like that. Just receives the log payloads and can print them, save them to a file, do that kind of stuff with the log messages that are received. And we've done various sort of micro benchmarks to validate this architectural approach. And there's a massive disclaimer in that this is not intended to be an accurate characterization of the performance you could get out of a dnstap-enabled DNS server under your production, realistic load. Various hardware details. Did fairly intelligent things. Disabling various things that might affect the results. Used a whole bunch of software, various tools for controlling the generating the traffic, controlling it, and measuring the performance. And basically, we just ran 30 or so data points, incrementing sending a particular DNS query load in 25 megabit steps, all the way from 25 megabits all the way up to 3/4 of a gig. And basically, all we do is just measure the total system load and the number of responses per second that the dnstap-enabled server is generating. It's interesting that most DNS benchmarks plot queries per second because they're interested in characterizing the drop rate. Here we're more interested in determining how much additional load that adding this dnstap support adds to the server, and this can still reveal interesting bottlenecks. So just to orient things, this is what a hypothetical good result and hypothetical bad result looks like. You have your purple plot. You have your x-axis, which is the number of queries answered per second, and we range from 0 all the way up to 1 million responses per second. And then system utilization ranges from 0 to 1, 1 meaning that all of the cores in the system are being occupied, 0 means obviously the system is completely idle. So your completely good hypothetical server consumes absolutely no CPU and answers every single query. And then your very bad server answers no queries and consumes all of your CPU. So that's the way these plots are oriented. Here are our baselines with this system for unbound 1.4.21 and unbound 9.9.4. This graph is kind of awkward to explain, since obviously one server appears to be performing about twice as good as the other one, so we see a fairly nice linear behavior from both of these servers. Well, obviously different slopes to those plots. So the actual query is to just the query load is to simply repeat the same query over and over again. And I suspect this may be more optimal for unbound than bind to answer. Here's what happens with bind 9. The purple plot is the baseline from the previous graph, and the red is what happens when you turn on query logging and tell it to write to a file on your disk. And, all the data points are concentrated towards the upper left of the graph, so it's shifting the performance in that direction. And obviously it's dropping a lot of queries under load compared to the baseline case where we're not doing any logging. Here's unbound. It performs basically about the same as bind 9 did. It has a steeper plot, and it's a performance barrier. And I think the reason for the behavior in both of these plots is simply that they're doing synchronous logging, and they're blocking the individual worker threads when they perform this logging. And that's specifically meant to address those points with a dnstap implementation. Here's our plot for unbound, the dnstap branch. We added dnstap support. The purple plot is the original baseline, and then the sort of teal colored is very close to it. That's with dnstap compiled in but disabled. And then the one right above that is compiled in and enabled, but discarding all of the log messages that are being generated. And then the top one is enabled and generating log messages, and there's a separate process receiving the dnstap messages and writing them to disk. And in contrast to the query logging plots, it's mostly manages to deliver a similar performance, but with additional CPU usage. So there's no the behavior is much closer to the base case with this implementation. So here's our summary. We tested 3 different recursive servers, original bind, original unbound, and unbound with this patch set that we've developed that implements dnstap support. Unbound generally scale better than by 9 in this particular benchmark on this particular hardware, but both servers implemented query logging in a way that significantly impacts the performance. And dnstap added some CPU overhead, but it tended to scale pretty well. And we have a certain amount of future work to do. We want to add additional payload types, we want to be able to trace cache events that are occurring inside a recursive DNS server. We want to add dnstap support to more software, obviously have better documentation, more tools and more benchmarks and actual specifications so that other people can implement this stuff as well. And that's it. We examined these two different use cases, and we introduced this new technology that can support both of these use cases with this message duplication facility. And that's all I have. Looks like a lot of time.
We have time for one quick question. You approaching the mic there? Okay.
Hi, my name is Daniel Karrenberg. I'm a DNS operator and measurer. Thank you for the talk. I think this has some potential to finally establish a common logging format across different DNS software, and that's why I like it. Yeah. So I would encourage you to work hard to get it incorporated in many DNS servers in the first instance. And I noticed that conspicuously absent from your list on like 5-6 slides back was NSD, the authoritative server from NANOG Labs. Is there a reason for that, or is that an oversight?
It's mostly a manpower issue. It just so happens that we looked at recursive DNS servers first, and out of recursive DNS servers, we looked at Unbound first. But it is our intention to add authoritative DNS servers, add support for authoritative DNS servers, including an NSD.
For my own I'm sorry, due to time considerations, I actually have to ask further questions to take offline. Sorry about that.
Okay.
Thanks, Robert.